Hello there, and welcome to another quiet night with the Sleepless Scientist. Tonight we'll wander into one of the strangest and most beautiful puzzles of all. The question of whether time itself continues to exist at the speed of light. If you enjoy this quiet wandering, a like or subscribe would mean a lot. Share where and what time it is. It feels like gathering round one fire. Now soften the room, let a hum keep you company, and let's begin. If you drift off, that's more than fine. Imagine yourself lying in the calm of evening. The day has ended, the sky outside your window perhaps holding a faint trace of fading light, or perhaps already deep into darkness. Time, for you, feels like a river that has carried you here. You can look back on the morning, on the many small moments that filled your day, and you can anticipate the hours that will follow until the next sunrise. Time is familiar, a gentle companion that shapes every heartbeat and every step. Yet tonight, we're going to stretch that river until it becomes something much stranger, until we ask whether the river is even flowing at all. The question we're exploring is deceptively simple. What happens to time at the speed of light? We know from everyday experience that when you walk, run, or even travel on an airplane, clocks continue ticking. Minutes pass, hours pass, and you remain inside the current of time. But light, those restless photons pouring from stars, bouncing off pages, shimmering in the glow of your phone screen, does not behave in the same way. For light, the universe may not have past and future, only an eternal now. It sounds poetic, but it is also physics. To understand why, we will need two companions, the photon, messenger of light, and the neutrino, the ghostly particle that comes tantalizingly close to sharing light's timelessness. Neutrinos are unlike almost anything else you will meet in science. They are tiny, nearly massless, chargeless wanderers that rush through the cosmos at nearly the speed of light. Right now, as you listen, trillions upon trillions of neutrinos are streaming through your body every second without pause, without resistance. They pass through your walls, your bed, the earth itself, barely acknowledging that matter is even there. They come from the nuclear furnaces of the sun, from the last breaths of distant supernovae, and even from the birth of the universe itself. For physicists, neutrinos are messengers. They carry stories of what happens in places no human eye could ever see, deep in the core of a star at the first instance after the Big Bang, or inside powerful particle accelerators. Yet for poets, and for those listening in the quiet of the night, neutrinos are almost dreamlike. Silent guests that travel with you at all times, witnesses to every moment, whispering secrets of the cosmos without ever speaking. Light, on the other hand, is both more familiar and more mysterious. You see by it, you feel warmth by it, and yet you rarely pause to ask what light actually is. Every photon has no rest mass. It cannot stop, not even for a fraction of a second. If a photon were to stop, it would cease to exist. This means that in the equations of relativity, a photon experiences no time. From the moment it is created, say in the fiery heart of a star, to the moment it strikes your eye, no seconds pass for it. The journey of billions of years across cosmic distances is, for light, nothing at all. That realization is already unsettling. We are creatures deeply tied to time. We measure birthdays, anniversaries, schedules, deadlines. We age, and with us the world ages. But the universe contains elements that are not bound in the same way. To a photon, the age of the cosmos is irrelevant. To a neutrino, almost as fast and nearly as elusive, time may be stretched so much that the difference between moments blurs into insignificance. And so, tonight's journey will drift between physics and philosophy, between what we can measure in laboratories and what we can only imagine. We will step slowly into the nature of time, ask what it means to live in a world where now is not universal, and follow light and neutrinos as they glide almost outside of time altogether. As you listen, you do not need to follow every formula or every scientific detail. let the ideas come gently, like waves at the edge of sleep. When a concept feels strange, hold it lightly, as you might hold a feather in your palm. If your mind wanders, let it wander. The photons still race, the neutrinos still pass through you, and the story will wait for you when you return. The question, does time exist at the speed of light, is not one with a simple yes or no answer. It is a doorway into the very structure of the universe. At human scales, time is our constant companion. At cosmic scales, time becomes flexible, bendable, and perhaps not fundamental at all. For the creatures of light, there is no past, no future, only an eternal instant. For neutrinos, there may be only a faint whisper of time, stretched so far that it almost disappears. And for us, time remains the stage on which we live, breathe, and dream. So as we begin, soften your thoughts. Picture yourself as a small traveller on a vast stage, with light as your companion and neutrinos drifting silently through you. Tonight, we will follow them into their strange, timeless world. Time has always been the quiet background against which we live our lives. But when you pause and really ask what it is, the question becomes slippery, almost like trying to catch mist in your hands. You can see its effects everywhere. Clocks tick, shadows stretch across the floor, bread goes stale, and children grow taller each year. Yet the essence of time, the thing itself, refuses to stand still long enough for a simple explanation. Philosophers, physicists, poets, and ordinary people waiting for a kettle to boil have all wrestled with it. Each generation, each culture, has found different ways to imagine what time means, and every attempt seems to reveal as much about ourselves as about the universe. In your everyday life, time appears orderly and predictable. You wake in the morning, perhaps to the sound of an alarm, and the hours seem to march forward in steady sequence. You go to work, eat lunch, feel the weight of the afternoon, and later, if you are lucky, you sink into bed at night. From this point of view, time feels like a river with a steady current, carrying you from sunrise to sunset. But if you pay closer attention, you will notice that the current is far from uniform. 10 minutes in a dull waiting room can stretch into what feels like half an hour, while 10 minutes lost in conversation with a friend can vanish before you realise they're gone. Time seems elastic, stretching and shrinking depending on the state of your mind. Psychologists sometimes call this subjective time. It is the personal sense of how long things take, and it is far less stable than the ticking hands of a clock. Memory plays a role as well. When you were a child, summers seemed endless. Days overflowed with novelty, new experiences, new places, new faces. Your brain recorded every detail, and looking back, those seasons appear vast and expansive. But as an adult, routine often compresses memory. The days blend together, and the brain does not bother storing every repeated detail. When you look back on a month, it can feel like it passed in the blink of an eye. To a brain trained by years of routine, time runs smoother, faster, and less memorably. Cultures have also shaped time in strikingly different ways. In ancient civilizations, time was often seen as cyclical. The sun rose and set, seasons turned in a loop, harvest followed planting, and death was followed by renewal. Time was like a wheel, endlessly rotating, returning always to the same point. In many indigenous traditions, this cyclical view remains strong. The past and future are not straight lines, but recurring rhythms that echo through generations. In contrast, in much of modern Western thought, time is imagined as an arrow. It shoots from a beginning toward an end, passing each moment once and never again. Progress, growth, and history all rely on this linear picture. Neither view is entirely right or wrong. They are different lenses through which human beings have tried to make sense of the same mysterious flow. Even language itself shapes how we think of time. In English, time is often treated like money. We spend it, save it, waste it, or run out of it. These metaphors nudge us into feeling that time is a commodity slipping through our fingers. But not all languages work that way. In some parts of the Andes, people gesture behind themselves when they speak of the future, because it is unseen, while the past is in front of them because it is known and visible. For them, the past is the landscape they face, the future is the unseen terrain behind their back. Such small shifts in metaphor can profoundly alter how time feels in daily life. Physics, of course, approaches the question differently. To Newton, time was absolute, a universal stage on which all events occurred, ticking away identically for everyone, everywhere. It was like a great invisible clock built into the universe itself. Later, Einstein overturned that certainty, showing that time is not the same for everyone, that it bends, stretches and slows depending on speed and gravity. We will come to that more fully later. For now, it is enough to note that even the deepest sciences cannot agree on a single definition. Time may be an illusion, or it may be the most fundamental thing we know, or it may be both at once. Yet beneath all the theories, the abstractions, and the mathematics, time always returns to experience. You feel it in the steady rhythm of your heart. You see it in the slow shifting of light across your room as evening deepens. You carry it in memories of days long gone, and in the anticipation of mornings yet to arrive. It is both external and internal, both measurable and intimate. Perhaps the most soothing way to hold time is to think of it not as something harsh or mechanical, but as a companion, a gentle one, though not always generous. It is the companion who reminds you that a cup of tea cannot cool instantly, that wounds take days to heal, that seeds in the ground need months to grow. Without time, there would be no unfolding, no music, no stories. The notes of a song require spacing, silence and rhythm. Without time, they would collapse into a single burst of noise. In the same way, your life would collapse without duration, without the gentle sequence that allows one breath, one step, one thought to follow another. And yet, as we will see, this companion is not as stable as we once thought. Under the gaze of relativity, and in the presence of light itself, time begins to dissolve. It becomes a flexible fabric, bending and changing depending on how you move through the universe. For photons, as we will discover, time may not exist at all. For neutrinos, the ghost particles drifting through you at this very moment, time is stretched so far that it almost vanishes. So hold that thought gently as we move forward. Time, in all its shapes and guises, may be the most personal thing you know, and the most puzzling thing the universe offers. Tonight we will follow it into strange places, into the speed of light, into the silence of neutrinos, and perhaps into a new way of seeing our own fleeting days. Close your eyes for a moment and picture the most ordinary source of light you know. It could be the warm glow of a bedside lamp, the steady beam of a streetlight outside your window, or the soft golden spill of sunlight through curtains on a slow morning. To you, light is background, always present, rarely questioned. You flip a switch, and there it is, filling the room, showing you the pages of a book, the familiar contours of your hand, the pattern on your pillow. But what exactly is this thing we call light? What is the substance of that glow? To begin our journey toward the mystery of time at its edge, we must first meet light on its own terms, and that means getting to know the photon, one of the strangest and most fundamental entities in the universe. A photon is, at first glance, simply a particle of light. That is the language you will often hear in popular science books and classrooms. But calling a photon a particle is a little misleading. It is not a tiny marble with weight and shape that you could hold between your fingers. In fact, a photon has no rest mass at all. Unlike every ordinary object around you, it cannot ever be still. If it stopped moving, it would cease to exist. Motion is its only mode of being. That already sets it apart from the world you know, where stopping is always an option. Sit in a chair, lie in a bed, pause to catch your breath. For a photon, there is no chair, No rest, no pause, only endless travel. Yet calling a photon a wave is equally incomplete. Light behaves like a wave in many experiments. It interferes with itself, it spreads through space in rippling patterns, and it can be described as an oscillation of electric and magnetic fields dancing together. Imagine two invisible partners, perpendicular to one another, vibrating in perfect synchrony as they race forward. This is the electromagnetic wave at the heart of light. But when light interacts with matter, it often behaves like a particle, striking one atom and not its neighbour, arriving in discrete packets of energy. The photon is not fully wave, not fully particle, but something that slips between categories. One way to soften this strangeness is to think of the photon as a messenger. It carries energy from one place to another. It carries information about the colour of a flower, the surface of a distant star, the smile of a loved one. It is a courier moving at the only speed allowed to it, roughly 300,000 kilometres every second. To put that into perspective, if you were somehow able to sit beside a photon as it left the sun, you would arrive on Earth about 8 minutes later. If you instead asked that photon to circle the globe, it could run around our planet more than 7 times in a single second. This is swiftness, beyond comprehension, and yet it is ordinary, happening in every instant around you. The photon is also astonishingly democratic. Light comes in many forms, from the long, lazy wavelengths of radio waves to the sharp, energetic spikes of gamma rays. The rainbow you see after a storm, the X-rays used in a hospital, the microwave oven humming in a kitchen, all are different flavours of the same underlying phenomenon. And yet, no matter how energetic or how long the wavelength, all photons travel at the same speed in a vacuum. The radio photon drifting from a tower and the gamma photon born in the heart of an exploding star both keep the same relentless pace. That speed is not chosen arbitrarily. It is written into the very fabric of the universe. Your eyes happen to be sensitive to only a narrow band of this great spectrum. That is what we call visible light, a mere sliver of the cosmic piano keyboard. Red light stretches longer and slower, violet light quicker and tighter, but all of it is part of a vast continuum extending in both directions beyond your vision. When you see a rainbow, you are seeing only a tiny glimpse of what light can be. If you could see beyond, into radio waves or into ultraviolet, the world would look utterly different. Another curious property of photons is that they do not need anything to travel through. Sound requires air. Water waves require liquid. But light moves freely in a vacuum. That's why you can see stars across enormous emptiness. Those photons left their stellar homes thousands, millions, or even billions of years ago, and they have crossed intergalactic space to arrive gently at your eye. Between their origin and their arrival, there was no stopping point, no resistance, only the endless dark of space. And here is a thought both poetic and disquieting. For the photon, there is no passage of time between leaving its source and arriving at its destination. The 8 minutes between Sun and Earth that you might measure on a clock do not exist from the photon's point of view. The billions of years from a distant galaxy to your telescope are, for the photon itself, nothing at all. That is because at the speed of light, time dilates completely. For light, there is no before and after, no waiting, no duration. The whole journey is collapsed into a single eternal instant. Pause to let that settle in. Imagine a photon leaving a supernova explosion at the edge of the observable universe. Billions of years pass for us as galaxies form, stars burn out, civilizations rise and fall. Yet for that photon, the moment of departure and the moment of arrival are one and the same. It carries no sense of the ages it has traversed. This timeless quality of the photon is at the heart of why we must rethink time itself when we confront the speed of light. If all of this sounds abstract, bring it back to something ordinary. Right now, photons are bouncing off the walls of your room, glinting from the edges of your cup, streaming in from lamps or screens. Each one is an eternal traveller, never pausing, always moving. They make sight possible. They define colour. They warm your skin in sunlight. And though they are so ordinary you rarely stop to notice, each photon is also a miracle, massless, timeless, a restless courier whispering the story of the universe directly into your eyes. And so, as we continue, keep this image close. Photons as restless travellers, particles that cannot stop, waves that do not need a medium, messengers that cross unimaginable gulfs only to arrive as if they had never left. They will be our guides into the strange softening world where time itself begins to blur. When you step outside on a clear evening and look up at the sky, the light of stars pours gently into your eyes. You may not think about it, but each one of those tiny points is a message travelling at the fastest speed nature allows. Nothing can outrun it. No rocket, no sound, no dream of human technology has ever broken that barrier. The universe, in its quiet, mysterious way, seems to have drawn a line in the sand. That line is the speed of light. Roughly 300,000 kilometers every second, or about 186,000 miles each second. It is a number so large that your imagination falters. Yet for the cosmos, it is not just a number. It is the ultimate rule, a limit inscribed into the structure of reality itself. Why does light move at this speed and not another? The answer begins with a deep partnership between electricity and magnetism. In the mid-19th century, James Clerk Maxwell discovered that when electric fields change, they give rise to magnetic fields, and when magnetic fields change, they generate electric fields in return. This mutual embrace creates a self-sustaining wave, moving outward forever. When Maxwell wrote down his equations, he found something astonishing. They predicted that these electromagnetic waves would travel at a single, specific speed, determined only by the properties of empty space. When he calculated it, he realized the number matched the known speed of light. Light, it turned out, was an electromagnetic wave, and its speed was not arbitrary, but woven into the very fabric of the vacuum. This speed soon became more than a curious fact about light. It became the keystone of relativity. Imagine you're on a train moving smoothly down the tracks. If you toss a ball forward, its speed relative to the ground is the speed of the ball plus the speed of the train. That feels obvious. But if you shine a flashlight forward, you might expect the same. The light should move at its own speed plus the train's speed. Yet every experiment, no matter how carefully done, shows that this is not the case. Light always moves at the same speed, regardless of whether you're on a rushing train, a speeding spaceship, or standing still in your kitchen. It is as though the universe refuses to let anyone or anything change light's pace. Albert Einstein, in his special theory of relativity, took this strange fact and built a new picture of the world. If the speed of light is always the same for everyone, then space and time themselves must bend to make it so. Distances contract, clocks slow, simultaneity becomes relative, all to preserve that one constant. The universe adjusts itself to ensure that nothing surpasses or alters the speed of light. In this way, light is not just another phenomenon, it is the cosmic metronome, the beat that every other movement must follow. To bring this strangeness into an everyday metaphor, picture yourself walking along a moving walkway at an airport. If you stroll forward, your speed relative to the ground is your own walking speed plus the walkway's motion. But imagine a world in which no matter how fast the walkway moved, no matter how briskly you walked, your speed relative to the ground never changed. The laws of physics would have to twist themselves to preserve that rule. That is, in essence, what happens with light. The walkway, the runner, the ground, space and time themselves must adjust so that the photon always keeps its pace. The limit is not just about light. It applies to everything. Any object with mass, from a feather to a galaxy, can approach the speed of light but never reach it. As it accelerates closer, more and more energy is required. The equations show that to reach the exact speed of light, an infinite amount of energy would be needed, something the universe simply does not allow. For ordinary matter, the speed of light is not just difficult, it is impossible. This is why the photon is unique. Having no rest mass, it is freed from the need to accelerate. It simply exists at that speed, moving through space as though it has no choice in the matter. And so, light becomes the boundary between what is possible and what is forbidden. It is like the horizon of a great ocean. You can sail as close as you like, but you can never cross it. The very act of approaching reshapes your experience of time and distance. Astronauts travelling near the speed of light would see their clocks slow relative to Earth, their journeys compressed compared to the experience of those who stayed behind. For them, the stars would draw nearer quickly, while for the people at home, decades might pass. This strangeness is not science fiction. It is measured in laboratories, observed in the behaviour of fast-moving particles, and relied upon in the functioning of technologies like the Global Positioning System. Satellites orbiting Earth tick more slowly than clocks on the ground, and their signals must be corrected for relativity to keep your maps accurate. Think of what this means. When you check your phone for directions, the device quietly accounts for the bending of time in orbit, the warping of space and clock rates, all to guide you to a cafe down the street. Einstein's deep insight, born from pondering the constancy of light, is woven into the fabric of your everyday life. But beneath the practicality lies something more profound. The speed of light is not just a speed. It is a universal constant, a kind of cosmic agreement. It ties together space and time into one fabric, what Einstein called space-time. It determines the structure of causality, what events can influence others and which are forever out of reach. When you look at the night sky, you're not just seeing stars, you're seeing the limits of influence, the boundary set by that speed. The light reaching you has travelled across immense distances, obeying the same rule for every observer everywhere. Pause and reflect on this. The universe did not need to give us a maximum speed, yet it did. That rule creates order out of potential chaos. Without it, signals could arrive instantly from anywhere, cause and effect could blur, and the cosmos would lose its rhythm. With it, there is structure, there is sequence, there is a stage on which the play of existence unfolds, not all at once, but with a steady, ordered beat. So the next time you flick on a light switch, consider what you are summoning. Not just brightness to see by, but the deepest principle of nature, the one rule that unites every corner of the cosmos. In that glow, humble though it may seem, lies the ultimate speed, the barrier that defines what can be known, what can be touched, and what must remain forever distant. And as we journey deeper into the story of light and time, keep that in mind. This limit is not a restriction to lament, but a rhythm to be grateful for. It is the reason galaxies have shapes, the reason cause follows effect, the reason your heart can beat one moment after another. In the quiet presence of light speed, the universe finds its harmony. Imagine standing on a train platform. A train thunders by, its windows flashing past you, each carriage a blur of motion. From your perspective, the people inside seem to move quickly, perhaps laughing or sipping from a cup as the world streaks around them. Now imagine instead that this train is not ordinary, but one capable of approaching the speed of light. If you could somehow watch closely, you would notice something strange. Their clocks would tick more slowly than yours. Their gestures would seem drawn out, stretched like a film played in slow motion. For you, moments would pass at their usual pace, but for them, time itself would be altered. This is the heart of time dilation, one of Einstein's most profound gifts to our understanding of the universe. Einstein's special relativity tells us that time is not an absolute drumbeat, ticking away identically for all. Instead, time depends on motion. The faster you move relative to someone else, the more your sense of time diverges from theirs. This is not an illusion. It is not a trick of perception. It is real, measured, and undeniable. The equations are straightforward enough. The closer an object moves to the speed of light, the more dramatically its time slows compared to that of a stationary observer. But equations are not what you need at night, in a quiet room. What you need is a way to feel this strangeness in your imagination. Picture two twins. One remains on Earth, living through the ordinary cycle of days and nights, years and seasons. The other boards a spaceship capable of near-light travel. Off they go, accelerating through the void, watching stars bend and shift under the influence of their speed. When the travelling twin returns, something extraordinary has happened. Though both felt time flowing normally as they lived it, the twin who travelled has aged less. Their clock ticked more slowly, their body accumulated fewer years. It is as if the universe itself rewarded the traveller with extra slices of youth, not by magic, but by the simple consequence of motion near the ultimate speed. This famous thought experiment is called the twin paradox, though it is not truly a paradox at all, merely a reflection of how relative time becomes at high velocities. You might wonder, does this really happen, or is it just theoretical poetry? The answer is that it happens, and it is measured every day. Subatomic particles created in the upper atmosphere by cosmic rays travel toward Earth at speeds close to light. Their natural lifetimes are so short they should decay long before reaching the ground. Yet because they are moving so quickly, their clocks are slowed relative to us. They survive long enough to be detected, living extended lives by virtue of their speed. Without time dilation, many of these particles would vanish before ever reaching a detector. Instead, they whisper proof of relativity with every arrival. Time dilation is not confined to cosmic rays. We see it in laboratories, where particle accelerators hurl protons and electrons to nearly light speed. Their lifetimes stretch, their behaviours change, all in precise accord with Einstein's equations. Even in the practical world, relativity quietly makes itself known. The satellites of the Global Positioning System circling Earth at high velocities experience time slightly differently than clocks on the surface. Engineers must correct for this difference, adding and subtracting nanoseconds each day, or else your phone's directions would drift, placing you streets or even miles from your true location. The corrections are tiny in everyday terms, but they are crucial. Relativity is not just a theory etched in textbooks. It is a tool embedded in your daily life, silently at work when you search for a cafe or find your way home. Pause for a moment and imagine what it feels like for the astronaut twin, moving through space. To them, life seems unchanged. Their pulse beats, their meals arrive, they drift into sleep and rise again. Their sense of time is smooth, unbroken. It is only when they compare with their sibling on Earth that the difference becomes clear. In that comparison lies the strangeness of relativity. There is no universal time, no master clock. Each observer carries their own rhythm, and those rhythms can diverge. This invites a gentle reflection. You may think of your days as fixed, an hour being an hour, a second being a second. But the truth is softer and more flexible. Even without rockets or relativistic speeds, your experience of time is already relative. A sleepless night stretches endlessly. A joyful afternoon evaporates in what feels like minutes. Physics confirms what your heart already suspects. Time is not rigid. It bends, it stretches, it can even nearly vanish. And then there is the edge, the place where time dilation becomes absolute. As an object approaches the speed of light, the slowing becomes extreme. Push further and further, and time nearly halts. At the ultimate speed, the photon's speed, time ceases to exist entirely. For light, there is no duration. Emission and absorption collapse into one moment. A photon leaving a star and arriving at your eye across billions of years has experienced no passage at all. That is the horizon we are heading toward in this journey, the place where time itself seems to evaporate. Before we go there, let us savour the strangeness we already have. The universe is not built on absolutes, but on relationships. Time is not a single thread running through everything at once. It is a web of threads, woven differently for each observer, stretching and bending depending on motion. You may never board a spaceship travelling near the speed of light, but in your body right now, trillions of neutrinos are doing something very close. They skim the edge of light speed, their clocks running so slowly that they seem nearly timeless. They are living examples of relativity, coursing through you at every instant. And so, as you drift deeper into this story, remember, when you check the time, when you feel the drag of minutes at work or the rush of an evening with friends, you're feeling a local, personal thread of time. But out there, in the vastness of space and in the tiny corridors of particles, time is not the same. It is slower, faster, or gone entirely. The universe allows each traveller their own tempo. Yours is human and steady. Theirs may be ghostly, stretched, or eternal. Close your eyes for a moment and imagine a star. Not just any star, but one far beyond our galaxy, so distant that its light has been travelling for billions of years to reach you. From our human perspective, that journey is almost unfathomable. Entire civilizations could rise and fall in the time it takes for that starlight to finally arrive at Earth. Galaxies collide, planets form, life emerges, and all the while, those photons stream forward, crossing an ocean of darkness that makes even the largest human voyage seem like a drop in the sea. You look up, and you see a twinkle in the night sky, and what you're really seeing is history. A message, launched long before the Earth even took the shape you now stand upon. But here is the twist, the strange, quiet miracle. For the photon itself, there was no journey. There was no time spent travelling across gulfs of space. From the instant it was emitted in that distant star to the instant it arrived in your eye, no seconds passed. The photon does not experience the billions of years that we measure. For light, emission and absorption are not separated by ages but are the same moment, the same now. This is one of the most unsettling and beautiful insights of relativity, that at the speed of light, time as we know it ceases to flow. We live inside time's current, always carried forward, unable to pause or step aside. You wait for bread to rise, for children to grow, for the seasons to change. Every activity has a before, a during, and an after. Even this story you're listening to is stretched across time. Words following words, ideas unfolding like a gentle ribbon. But for the photon, there is no before and after. It is as though light slips out of the river of time entirely, skating across the surface without ever touching its flow. This creates a peculiar image. Imagine the universe as a vast canvas, a frozen painting filled with stars and galaxies. For us, that painting is constantly changing. New brushstrokes appear, old ones fade, whole swaths are repainted as moments pass. But for light, that painting is already complete, a single eternal image. The photon does not watch the painting change. It simply exists within the completed picture, from point of origin to point of arrival, as though all of history were compressed into one infinite instant. If that feels abstract, let us bring it closer. Consider sunlight. The photons that warm your face in the morning left the surface of the sun about 8 minutes earlier. For you, 8 minutes is a length of time you can feel. You could boil an egg, take a short walk, or wait for a bus. For the photon, however, there was no wait. The instant it left the sun's surface, it also arrived on your skin. The 8 minutes collapse to zero, to light, distance shrinks, and time evaporates. The implications are staggering. When you gaze at the faint glow of a galaxy billions of light years away, you're witnessing something ancient. Yet for the photons themselves, there was no delay. They were emitted and received in one continuous timeless act. The story of the cosmos, as told by light, is not a sequence, but a single gesture. A hand extended across eternity and held open until you look up. Think of a letter sent by post. You write it, place it in an envelope, and send it across the country. Days pass. You may even forget about it until the reply arrives. But for the photon, there is no postal delay. The letter is written and delivered in the same breath. That is what it means to move at the speed of light. The journey is collapsed, the waiting erased, the passage through time dissolved. This is not to say that photons are conscious, or that they feel timelessness. They are not minds with awareness, but their behaviour tells us something profound about reality. Time, which seems so absolute to us, is not universal. It bends and breaks depending on speed and perspective. From our point of view, billions of years roll by. From light's perspective, there is only a single frozen instant. Both perspectives are true, and both exist at once. It may help to imagine yourself as a small observer perched on the back of a photon. You launch from a star, and in that instant you also arrive at Earth. You do not sense the turning of galaxies, the birth and death of stars, the flow of eons. For you there is no ticking clock, no long voyage, only departure and arrival, simultaneous and inseparable. The cosmos shrinks into a single step. The great distances that separate galaxies dissolve, not because the space is gone, but because the time to cross it has collapsed to nothing. Contrast this with your own experience. For you, the universe is alive with duration. You wait, you anticipate, you remember. Time is the medium of your life, the silent partner that makes every story possible. You cannot imagine being outside of it, because even imagination itself requires the unfolding of thought from one moment to the next. To be a photon is to live without that unfolding, without the river, without the clock. It is to exist only in an eternal now. And perhaps this is what makes light such a profound teacher. It shows us that time is not a single universal flow, but a relative, malleable thing. It can stretch, shrink, or disappear, depending on the path taken through the universe. When you see light, you are not just seeing brightness. You're glimpsing a way of being that is alien to your own. A life without waiting, a journey without passage. So the next time you stand under the stars, pause and let the thoughts sink in. The light that reaches you has crossed the universe, carrying the memory of ancient fires. For you, it was a long journey. For the photons themselves, it was no journey at all. They have been outside of time, slipping past the very thing that defines your life. And as you breathe and listen, you may find comfort in that. Even in the vastness of space, where distances seem insurmountable and time stretches beyond comprehension, there is something that knows no delay, something that connects the beginning and the end in one eternal gesture. Imagine for a moment that you are running. At first your strides are light, your breath steady, the air cool against your skin. With every step you add speed, pushing harder, legs pumping faster. At first the effort feels manageable, but as you continue, the resistance builds. Your lungs burn, your muscles ache, and though you add more effort, the increase in speed grows smaller. Now imagine that the air itself has turned thick, like molasses. Each attempt to move faster feels like pushing through syrup. At some point, no matter how desperately you try, you cannot go faster. Your body demands infinite strength that you simply do not have. This picture, familiar in its exhaustion, mirrors what happens in the universe as anything with mass tries to reach the speed of light. Physics tells us that as an object moves faster and faster, something curious happens to its energy. In the equations of relativity, the kinetic energy required to increase velocity does not rise gently or even steeply. It rises toward infinity as the object approaches light speed. Imagine trying to fill a cup, but the cup grows larger the more you pour, always demanding more water. No matter how much energy you provide, the object always requires more. An unending hunger that makes reaching the speed of light impossible. This is why light is unique. Photons, having no rest mass, never need to accelerate. They are born at the speed of light and exist there perpetually. They do not struggle against molasses, they simply glide in their eternal state. For everything else, from protons and electrons to people and planets, that horizon is out of reach. We can approach, we can come close, but we cannot touch. The closer we move to light speed, the more energy we must pour in, until the demand becomes infinite. The barrier is absolute. Think again of the twin paradox from earlier. The travelling twin zooms near light speed, their time slowing compared to their sibling on Earth. Yet no matter how powerful their spaceship, no matter how advanced the engines, they cannot quite reach the ultimate speed. Their time slows, but it never freezes entirely. There is always a gap, a fraction separating them from timelessness. The photon inhabits that realm effortlessly. The rest of us can only circle its edge. It is tempting to imagine that one day, with enough technological brilliance, humans might find a loophole, perhaps an engine of unimaginable power, perhaps a warp in space-time itself. But the laws as we understand them today are stubborn. They whisper a firm no, light speed is not just a practical barrier, but a fundamental one, rooted in the very geometry of space-time. Just as you cannot divide by zero in mathematics, you cannot accelerate a mass to the speed of light in physics. The structure of reality itself resists. This resistance gives shape to our universe. If nothing had such a limit, cause and effect would blur. Information could leap instantly from one place to another, and the fabric of events would lose its coherence. The speed of light is not merely an inconvenience for spacefarers, it is the rule that keeps order in the cosmos. By limiting how fast influences can travel, it preserves causality, ensuring that effects do not precede their causes, that the universe remains a story told in sequence rather than chaos. And yet, within this limit there are edge cases, particles so small and so swift that they live close to the horizon. Among them are neutrinos, those ghostly travellers that flow through you in unimaginable numbers every second. Neutrinos possess mass, but only the barest whisper of it. They move at speeds just below light, so close that for them, time stretches almost to nothing. Unlike photons, they cannot escape time entirely, but their experience is far removed from ours. Where we live in minutes, hours, and years, neutrinos live in stretched instants, each moment drawn long by their speed. To prepare for them, let us return to the image of molasses. Imagine that instead of plunging into the thick syrup, you are made so light, so insubstantial, that you nearly skim across the surface. You still feel resistance, but barely. Your body still carries mass, but it is so faint that you almost escape its burden. That is the neutrino's condition, not timeless like light, but living on the very edge of timelessness, brushing against the boundary the rest of us cannot reach. The edge of the possible is therefore a kind of paradoxical space. It is forbidden for us, but ordinary for light. It is unreachable for matter, yet constantly skirted by neutrinos and other high-energy particles. It is both the strictest law and the most generous gift. It ensures stability in the universe, and at the same time, it fills our skies with messengers that remind us how strange that stability truly is. You may wonder what it would feel like to approach that edge yourself. Picture boarding a spacecraft built to accelerate steadily, day after day, until you near light speed. For you inside, time would seem normal. Your meals, your dreams, your conversations unfolding at their usual pace. But compared to Earth, your clock would tick more slowly. Days on board might correspond to years at home. The faster you travel, the more extreme the difference becomes. Push closer still, and Earth might spin through decades while you age only months. But no matter how powerful the ship, you would never arrive at the horizon. The closer you came, the more the universe demanded of you, until the very concept of reaching light speed dissolved into impossibility. And so, there is a kind of poetry in this limit. It humbles us, reminding us that we are bound creatures, tethered to time in ways light is not. Yet it also opens the door to wonder, because on this edge, in the thin space between mass and masslessness, live the neutrinos, the particles that embody both mystery and possibility. They are the almost photons, the near-timeless travellers, slipping through walls and mountains as if the universe itself has made them exempt from ordinary rules. They live where our imagination struggles, and in their near-light journeys they carry whispers of cosmic history. As we leave the photon's perfect timelessness and stand before the barrier that forbids us entry, we now turn toward those ghosts. To understand them is to glimpse what it means to almost live outside of time, to brush against the horizon of the possible, and to see how even the smallest particles can tell the greatest stories of the cosmos. Imagine lying still in bed, the room quiet, the hum of the world softened into the background. You may feel alone, cocooned in the hush of night, but in truth, you are never alone. Right now, in this very moment, trillions upon trillions of invisible travellers are streaming through you. They slip through your body without pause, without resistance, without even a whisper of acknowledgement. They pass through your walls, through your bed, through the earth itself, as if matter were nothing more than a faint shadow. These are the neutrinos, the ghost particles of the cosmos, and though you may never notice them, they are among the most abundant companions you will ever have. Neutrinos are tiny beyond comprehension. They are not made of smaller parts the way protons and neutrons are. They are fundamental, indivisible in the picture of physics we currently hold. They carry no electric charge, which means they do not interact with the electromagnetic forces that bind atoms and molecules together. They do not cling to electrons, do not spark with magnetism, do not shimmer with light. Their masses are so minuscule that for decades, scientists believed them to be completely massless. Only later did careful experiments reveal that neutrinos do in fact possess mass, though so slight that it is almost beyond measurement. In many ways, they are the closest things in the material world to being pure whispers of existence, flickers that almost escape the rules of matter. Where do they come from, these silent companions? The answer is everywhere. The nuclear fires at the heart of the sun are perhaps their most abundant source in your daily life. Each time hydrogen fuses into helium, releasing the sunlight that warms your skin, neutrinos are also born, streaming outward in colossal numbers. By the time they reach Earth, about 65 billion solar neutrinos pass through every square centimetre of your body every second. That is not a typo. 65 billion through each fingertip, through the space behind your eyes, through the soles of your feet, every single second. And almost none of them ever touch you in any meaningful way. But the sun is only one forge. Neutrinos are also born in the cataclysms of dying stars, in the heart of supernovae where gravity crushes matter into extremes no laboratory could hope to imitate. They emerge in the first seconds of a nuclear explosion. They are manufactured in particle accelerators, in reactors, in every place where protons and neutrons collide or transform. They are woven into the very story of the universe's birth. In the first second after the Big Bang, when the cosmos was hotter and denser than any fire you can imagine, neutrinos were produced in such vast numbers that their echoes still linger today, a faint background hum that physicists believe permeates all of space. To picture a neutrino, think of a ghost moving through a crowded ballroom. People dance, the orchestra plays, chandeliers sparkle, but the ghost is untouched. It drifts between couples, through tables, across the floor, invisible and unbothered. That is what neutrinos do in the universe of atoms. They ignore almost everything. passing through billions of miles of solid matter without stopping. Once in a great while, by sheer accident, one may strike an atomic nucleus, leaving behind a faint trace that our instruments can detect. But such encounters are rare. Most neutrinos travel through the cosmos unseen, carrying their secrets intact. This makes them both frustrating and beautiful to study. Frustrating because they are so hard to catch. Scientists build vast detectors, filling tanks with pure water or heavy liquids, burying them deep underground or under ice to shield from background noise. Even then, most of the passing neutrinos slip by unnoticed, ghosts unwilling to be pinned down. Beautiful because the ones that do leave a trace give us direct information about places we cannot otherwise reach. Neutrinos are perfect messengers. They do not scatter easily. They do not get deflected by magnetic fields or absorbed by interstellar dust. They emerge from the densest hearts of stars and carry with them unedited original stories of what happened inside. And here is where they become truly astonishing. The neutrinos passing through you right now may have been born in the centre of the sun just a few minutes ago, in a nuclear reaction that released both a burst of sunlight and a whisper of neutrino. Others may have left a supernova thousands of light years away, travelling across the galaxy in straight, unwavering lines. Others still may be ancient, forged in the first flicker of the cosmos, older than stars, older than galaxies, older than Earth itself. To host them, to feel their endless passage, is to be touched constantly by the deepest history of the universe. Yet despite their ghostly nature, neutrinos do have weight in the grand scheme of things, because there are so many of them, countless, immeasurable, more abundant than the stars. They contribute to the overall balance of matter in the cosmos. Their tiny masses add up, and their relentless motion helps shape the formation of galaxies and clusters. Invisible though they are, they tug ever so slightly on the evolution of the universe. If photons are the storytellers of the visible cosmos, illuminating what we can see and measure, neutrinos are the secret scribes. They carry accounts of events hidden from light, of nuclear reactions deep within stars, of processes at the very birth of time, of forces that remain beyond our comprehension. To meet them is to realise that you are permeated by history, that every second of your life is threaded through with visitors older than memory. The next time you feel alone in the dark, remember this: you are never untouched. Streams of neutrinos pass through you, constantly, silent witnesses of creation, ephemeral travellers that have crossed gulfs of space and oceans of time to arrive here, in this quiet moment, with you. You are quite literally a crossroads of the universe. If neutrinos are the quiet travellers of the cosmos, then their most dramatic stories come from moments of violence, from the great convulsions of the universe when stars die, or when matter is pushed to its breaking point. Though they themselves are almost weightless and silent, they are born in fire and collapse in events so cataclysmic that even the hardest metals and the strongest rocks would be reduced to vapour. They are paradoxical in that way, the gentlest of particles, yet messengers of the most violent transformations the universe has ever known. The most famous example in modern astronomy came in 1987, when a star in the Large Magellanic Cloud, a neighbouring galaxy to our own, reached the end of its life. This star, unimaginably larger than the Sun, had exhausted the nuclear fuel at its core. Without the outward push of fusion to hold it up, gravity won. The core collapsed in a heartbeat, squeezing protons and electrons into neutrons, releasing an avalanche of neutrinos in the process. Then the outer layers rebounded and exploded outward in what we call a supernova. For anyone watching from afar, the event was breathtaking. A sudden new light in the sky, a beacon brighter than 1 billion suns. For the neutrinos, it was their moment of birth, a flood rushing out of the collapsing star. What makes this story extraordinary is that on Earth, detectors buried deep underground, vast tanks of water watched by sensitive instruments, recorded the arrival of those neutrinos. In fact, they arrived before the visible light of the explosion did. Light from the supernova had to struggle outward through layers of stellar material, scattering and delaying on its way. Neutrinos, indifferent to such obstacles, escaped almost immediately, reaching us within hours of the collapse itself. Astronomers, peering into their instruments, realized they had been given a gift. For the first time, humanity had caught neutrinos from beyond our solar system. Neutrinos carrying first-hand testimony of a stellar death. The event, called Supernova 1987A, changed the way we understand the universe. It showed us that neutrinos could act as cosmic early warning signals, announcing the death of a star before its light even arrives. Since then, observatories around the world have waited patiently, deep underground and beneath Antarctic ice, hoping for the next great burst of neutrinos. When the next nearby star dies, those ghostly particles will be the first to whisper of it, rushing to Earth in their silence, giving us a head start in understanding the explosion. But neutrinos do not only come from the death of stars, they also come from the beginning of everything. In the first seconds after the Big Bang, the universe was a roiling soup of particles and energy. It was so dense that photons could not travel freely. Light was trapped, scattering endlessly. Only after hundreds of thousands of years did the universe cool enough for photons to stream across space, leaving behind what we now call the cosmic microwave background. Neutrinos, however, escaped much earlier. Within the first second, they were already free, streaming outward, filling the universe with their presence. Those relic neutrinos are still with us today, faint and nearly impossible to detect, but they remain as fossils of the earliest moment of time. They are not just messengers of cataclysm, but witnesses of creation. Think of them as postcards from events we can never visit. A postcard from a supernova, telling us of a star's final scream. A postcard from the Big Bang, inked in the faint traces of neutrinos that have been travelling for nearly 14 billion years. Unlike light, which can be blocked or delayed, neutrinos carry their messages directly, unscattered, unaltered, honest in their silence. They are the straight-line historians of the cosmos, and so, when you lie in bed tonight, consider this. Within you and around you are neutrinos born from cataclysms far away. Some may come from a recent solar flare, others may come from a star that exploded before humans even walked the Earth. Still others may be as old as time itself, survivors from the first heartbeat of the universe. You're immersed in their presence, a living sea of invisible messengers that remind you that the universe is not calm but alive with events of staggering violence and beauty. There is a quiet poetry in knowing that your body, your bones, your very breath are being crossed every second by witnesses of such grandeur. You do not hear them, you do not feel them, but if you could, perhaps you would feel like a library filled with postcards, each one telling a story of collapse and creation, of endings that became beginnings. When astronomers describe neutrinos as messengers, it is not only a metaphor, they are literally carrying information. The most direct information we have from places no telescope could ever see. To look inside the core of a star is impossible with light. To glimpse the very first second of the universe is impossible with photons. But neutrinos go there, and they come to us. They carry their messages without adornment, without pause, and they deliver them to us every second of every day. The challenge, of course, is learning how to read them. Our detectors are like mailboxes waiting for a letter that may or may not arrive. Most neutrinos slip past, their postcards undelivered. But occasionally one strikes, leaving a faint trace of its passage, a signature in a sea of silence. From those faint scratches, those quiet ripples, we piece together stories that reshape our understanding of the universe. And so, the neutrino is not only a ghost, but also a herald. It announces births and deaths on scales that defy imagination. It is the whisperer of cataclysm, carrying postcards of explosions and creation, slipping through your body as though to remind you that you're never disconnected from the cosmos. The very fabric of the night is filled with their presence. When scientists first began to study the sun with neutrinos in mind, they expected the results to be straightforward. The sun is, after all, the most constant feature of our sky, a furnace burning with nuclear reactions that fuse hydrogen into helium. Each of those reactions produces neutrinos, tiny passengers slipping out almost instantly from the core, long before photons make their much slower escape. If our theories of stellar fusion were correct, then we should be able to predict how many neutrinos are born every second and therefore how many should wash across Earth. With this logic, scientists built detectors and waited, confident that the ghostly rain of neutrinos would match the numbers scribbled into equations. But when the first results came in, there was a problem. The detectors did not see the expected flood. Instead of the full banquet of neutrinos, they caught only a fraction, barely a third of what theory demanded. It was as though scientists had set a table for 100 guests, baked loaves of bread, poured wine, prepared seats, and yet when the evening arrived, only 30 guests showed up. The rest were missing, absent without explanation. The puzzle became known as the solar neutrino problem, and for decades it haunted physicists and astronomers alike. The detectors themselves were extraordinary pieces of engineering. In one famous experiment, a huge tank was filled with cleaning fluid. Yes, the very same perchloroethylene used in laundries. The idea was that every so often, one of the countless solar neutrinos passing through would collide with a chlorine atom, turning it into argon. Those rare argon atoms could then be extracted and counted, providing a tally of the neutrinos that had arrived. It was a clever approach, but the numbers kept coming back far too low. The sun, it seemed, was not sending enough neutrinos. But how could that be? Our entire understanding of nuclear fusion, of how stars shine, rested on the assumption that the sun must produce them in abundance. Some worried that perhaps our theory of the sun was wrong. Maybe fusion worked differently than we thought, or perhaps the core burned less brightly than our model suggested. But everything else about the sun, its light, its heat, its behaviour, fit perfectly with the theory. It was hard to believe that the sun itself was the problem. Others considered the detectors. Could the instruments be failing? Could the chemistry be mistaken? Could some crucial interaction have been overlooked? But repeated experiments with different techniques gave the same answer. Missing neutrinos. Always fewer than expected. For years, the problem loomed like a shadow over both astrophysics and particle physics. It was a quiet embarrassment, a mismatch between observation and theory that resisted every attempt at resolution. Scientists are used to puzzles, but this one endured. The sun, constant and reliable in every other respect, seemed to be holding back a secret. The eventual answer, when it arrived, did not come from a failing sun or broken detectors, but from the neutrinos themselves. The missing guests had not failed to appear at the banquet. They had simply changed their clothes, disguised themselves, and slipped past the head count. Neutrinos, it turned out, could change their identity in mid-flight. They come in 3 flavours: electron, muon, and tau neutrinos. The detectors had been designed to catch only electron neutrinos, the type expected from the sun's core. But as the neutrinos streamed outward through space, many of them transformed into muon or tau neutrinos, which the detectors could not see. The guests had arrived, but in disguise. This phenomenon, called neutrino oscillation, was revolutionary. It meant that neutrinos are not fixed in their identity, but can shift from one type to another as they travel. And if neutrinos can oscillate, they must have mass. A particle with absolutely zero mass cannot switch states in this way. The discovery that neutrinos have mass, however tiny, shook the foundations of physics. The Standard Model, our carefully constructed framework describing fundamental particles, had long insisted that neutrinos were massless. Here was proof to the contrary. The universe had whispered a correction, and it was one we could not ignore. Think of it in everyday terms. Imagine watching a marathon in which runners begin in bright red shirts. You count them as they pass, confident that every runner is marked by the same colour. But as the race goes on, some of those runners quietly slip into alleyways and change into blue or green shirts. When you count again at the finish line, the number of red shirts is far lower than expected. At first, you suspect some must have dropped out, or that you miscounted, or that the rules of the race were misunderstood. Only later do you realise that the runners themselves were not constant in appearance. They were the same athletes all along, but they changed their colours mid-race. That is what neutrinos do as they cross the gulf between the Sun and Earth. The resolution of the solar neutrino problem was more than just a scientific victory. It was a reminder of how subtle the universe can be, how even the most abundant and simplest seeming particles can harbour secrets that challenge our deepest theories. It also taught us humility. The Sun had not betrayed us. The detectors had not failed. It was our assumptions that were incomplete, our picture of the neutrino too rigid and simplistic. Once we allowed for flexibility, once we imagined that identity could be fluid, the pieces fell into place. And so, the missing neutrinos were never missing at all. They were with us all along, slipping through in different forms, invisible to the detectors of the time, but real nonetheless. Today, with improved instruments sensitive to multiple flavours, we can see the full picture, confirming that the guests are present at the banquet after all. They are simply shapeshifters, moving from one mass to another, reminding us that in the quantum world, identity is not as fixed as we might like to think. This discovery has implications that ripple outward into cosmology, particle physics, and philosophy. If neutrinos have mass, then what else might lie beyond the standard model? What new layers of reality might we uncover when we learn to listen more carefully to the universe's quiet messengers? If you were to line up the known particles of the universe like characters in a grand play, most of them would be easy to identify. Protons and neutrons sit proudly in the nucleus, bound together like sturdy bricks. Electrons whirl around, light-footed dancers carrying charge and shaping chemistry. Photons dart in and out, the nimble couriers of light. Each has its role, its costume, its name. Yet neutrinos are different. They slip into the play like tricksters, wearing masks that change from scene to scene, sometimes without warning. One moment, they are electron neutrinos, the flavour expected from the Sun's core. Another moment, they have become muon neutrinos, as though they stepped into a side room and changed attire. A little further on, they may appear as tau neutrinos, a rarer form, heavier in character. And then, almost casually, they switch again. This constant shape-shifting is what we call neutrino oscillation, and it is one of the most fascinating behaviours in modern physics. For decades, physicists believed neutrinos had no mass at all. They were thought to be pure ghosts, slipping through the world without the heaviness that defines ordinary matter. That assumption seemed sensible. After all, neutrinos were so elusive, so resistant to interaction, that imagining them as massless fit the picture. But the solar neutrino problem changed everything. To explain why detectors were finding only a fraction of the expected neutrinos, scientists realised that the particles must be changing flavours as they travelled. They were not vanishing, they were disguising themselves. And the ability to oscillate between states demanded that they have mass, however tiny. It was a revelation that rippled through physics, forcing us to rewrite parts of the standard model. The framework that had so elegantly described particles for decades. To understand oscillation, imagine again the marathon of runners we spoke of earlier. At the starting line, every runner wears a red shirt. Along the course, some slip into side alleys, changing into blue or green. When you count them at the finish, the colours no longer match what you expected. Now extend the metaphor. Imagine that the runners do not decide when to change shirts. Instead, their shirts shimmer between colours as they run, sometimes red, sometimes blue, sometimes green, as though the very identity of the runner is a blur in motion. That is what neutrinos do. Their flavour is not fixed but fluctuates with distance and time, a quantum uncertainty written into their being. This strange property arises because the flavour of a neutrino, electron, muon or tau, is not the same as its mass state. In the hidden mathematics of quantum physics, these states are like overlapping melodies. What you see in the moment depends on which notes are resonant. As neutrinos travel, the balance between these melodies shifts, and so their identity appears to change. They are never purely one thing or another, but mixtures, superpositions shimmering between forms. It is an invisible dance, but it plays out across every neutrino's journey through the universe. The discovery of oscillation came not from theory alone, but from experiments built in quiet places, often underground. One of the most striking was Super Kamiokande in Japan, a detector buried deep within a mountain, filled with 50,000 tons of pure water. Photomultiplier tubes lined its walls like watchful eyes, waiting for the faint flashes of light created when a neutrino occasionally collided with a water molecule. It was there that scientists confirmed that neutrinos from the atmosphere changed flavours as they travelled, shifting identities between sky and Earth. Other experiments in Canada and elsewhere confirmed the picture with solar neutrinos, showing that the missing guests had merely arrived in different costumes. Slowly the case became undeniable. Neutrinos oscillate. For the physicists who had long trusted the Standard Model, this was both thrilling and unsettling. The model had insisted neutrinos were massless. Oscillation proved otherwise. Though their masses are tiny, millions of times smaller than an electron's, they are not zero. And that non-zero mass opens the door to mysteries. Why do neutrinos have such peculiar properties? Why are their masses so small? Could they be clues to physics beyond what we know? In their quiet way, neutrinos were telling us that the play was larger than the script we'd written. To soften the strangeness, think of neutrinos as travellers on a long journey, carrying a trunk of costumes. Depending on where you encounter them, they may be dressed one way or another. They do not settle into a single identity, but rather reveal different faces to different audiences. And because they are so light, so fast, they cover vast distances while switching attire countless times. By the time a solar neutrino arrives at Earth, it has changed flavour many times, so what our detectors see is a mixture of identities, a kaleidoscope rather than a single colour. This shapeshifting is not just a curiosity, it is a vital key to understanding the universe. Because neutrinos are so abundant, their tiny masses collectively add up to something significant, influencing the way galaxies formed, the clustering of matter, the large-scale structure of the cosmos. If neutrinos had no mass, the universe might look different. Their small weight, multiplied by uncountable numbers, has helped shape the very architecture of the night sky you see above. And on a more intimate level, the story of oscillation reminds us of the beauty of uncertainty. We often like to imagine the world as clear and fixed, identities stable, roles defined. But in the quantum realm, identity itself can be fluid. The neutrino teaches us that being one thing does not exclude being another, that transitions and mixtures are as natural as solidity and clarity. Perhaps there is something quietly comforting in that. We too shift identities in our lives. Child, parent, student, teacher, friend, stranger, sliding between roles depending on where we are and who we meet. Neutrinos in their cosmic dance mirror that flexibility. So when you think of neutrinos now, do not imagine them as single, unchanging particles. Picture instead a troupe of dancers moving across a stage, costumes changing as the lights shift, never staying still, never bound by one identity. They are the masters of disguise, the shapeshifters of the particle world, the quiet reminder that even in physics, certainty is sometimes an illusion. And with that realization, we prepare to follow neutrinos further, into the heart of the cosmos, and into the hidden layers of time itself. They are no longer just ghosts passing through you. They are storytellers in disguise, carrying with them not just the secrets of stars and supernovae, but also the hint of a deeper physics waiting beyond the horizon of what we know. Close your eyes and imagine the universe not as it is now, filled with galaxies and stars, but as it was in its very first moments. No planets, no suns, no atoms even, only a seething ocean of particles and energy, hotter and denser than the core of a star, a newborn cosmos in the first second of its life, in that fiery instant, when temperatures were so high that matter itself quivered on the edge of existence. Neutrinos were already there. They were among the very first to step out into the open, slipping free of the tangled interactions that kept other particles trapped. While photons, the particles of light, were caught in a haze of endless collisions, bouncing around and unable to travel freely, neutrinos escaped almost at once, streaming outward into the vastness that was just beginning to form. These first neutrinos are still with us. They are known as the cosmic neutrino background, relics of the Big Bang itself. If you could somehow tune your senses beyond light, beyond sound, beyond the ordinary fields of perception, you would hear them as a faint hum filling all of space. They're unimaginably abundant, passing through every cubic centimetre of the universe, including the one your body currently occupies. They do not shimmer, they do not scatter, they do not announce themselves, yet they are there, silent witnesses to the very dawn of time. To appreciate their importance, think of an orchestra warming up before a grand performance. The strings are tuning, the woodwinds are testing their notes, the percussion is rattling softly. Amid this noise, a background hum arises, not a melody yet, but the foundation on which the music will soon be built. The cosmic neutrino background is that hum. It set the conditions for what followed. The birth of atoms, the gathering of galaxies, the cooling into structures we now inhabit. Without it, the cosmic music would have sounded very different. Detecting these relic neutrinos is nearly impossible. Their energies are low, their interactions so faint that they slip through detectors as though the instruments were made of mist. Yet scientists are confident they exist, not just because the theory of the early universe demands them, but because of the traces they left in the cosmic pattern. When we look at the cosmic microwave background, the afterglow of light released hundreds of thousands of years later, we can see subtle imprints of neutrinos woven into its fabric. Like fingerprints left on a canvas, these imprints whisper that the ghosts were there long before light was free to travel. The difference between photons and neutrinos at the dawn of time is striking. Photons had to wait until the universe cooled enough for atoms to form. Before that, they ricocheted endlessly off free electrons trapped in a fog. Only after about 380,000 years did they escape, creating the cosmic microwave background we now observe with telescopes. Neutrinos, on the other hand, slipped free after only 1 second, racing outward with no regard for the fog. That means they have been travelling unimpeded for almost the entire age of the universe. Imagine a marathon where one runner is released at the starting gun, while another is forced to wait behind a locked gate for 380,000 years. When the gate finally opens, the first runner is already so far ahead that catching up is impossible. That is the story of photons and neutrinos. If photons are the visible record keepers of the cosmos, neutrinos are the secret scribes, writing their chronicles in silence long before light could take its first step. They shaped the density and the rhythm of the early universe. Because they moved so freely, they carried energy outward, smoothing out differences, affecting how matter clumped together, influencing which regions would later grow into galaxies and which would remain sparse. Though they are nearly invisible now, their touch is etched into the very arrangement of the universe. To put it differently, neutrinos are like the scaffolding that builders set up before raising a cathedral. You may never see the scaffolding once the structure stands, but without it, the walls and towers would not have risen as they did. The neutrinos of the early universe were part of that invisible scaffolding. They guided the cosmic construction, ensuring that galaxies, clusters and filaments formed in the patterns we now see stretching across billions of light years. Even though they are beyond direct detection today, the very thought of them is humbling. The breath you take right now, the stars you see tonight, the galaxies painted across telescopic images, all of it has been influenced by the presence of relic neutrinos. Every corner of space, no matter how empty it seems, is filled with their quiet passage. They are like a memory that never fades, woven into the background of everything. If you listen carefully, in imagination rather than in sound, you might almost hear them. Not as noise, not as voices, but as a soft vibration beneath existence. A hum too deep for ears, too subtle for eyes. The universe has never been without them. They were present at the first heartbeat of creation, and they are present here, in this quiet moment, as you rest. To realise this is to feel the immensity of connection, to sense that you are not separate from the cosmos, but immersed in its story from the very beginning. So the next time you look up at the stars, remember that the light reaching you began its journey long after the neutrinos already set out. You're touched by both, by the brilliance of photons and by the ghostly passage of neutrinos, the early and the late messengers of the cosmos. One dazzles you with brightness, the other slips unnoticed through your skin. Together they tell the whole story. A universe that began in fire, cooled into matter, and still carries its earliest echoes everywhere. When you look at the night sky, perhaps lying back in a field or peering out of a window at midnight, you see patterns of light, constellations drawn by human imagination, clusters of stars gathered in hazy patches, the faint smudge of the Milky Way stretching across the heavens. What you do not see, at least not directly, is the vast cosmic architecture behind those pinpricks of light, the filaments of galaxies, the webs of dark matter, the immense structures that span hundreds of millions of light years. This grand design did not simply appear by chance. It was shaped by countless subtle influences, one of the most important of which came from the ghostly neutrinos that slipped free of the universe almost as soon as it began. We often imagine neutrinos as solitary travellers, streaming quietly through us, passing unnoticed. Yet when they are considered collectively, their numbers are so staggering that they wield influence on scales far larger than a human mind can comfortably grasp. There are more neutrinos in the universe than any other type of particle, except perhaps for photons. Every cubic centimetre of space contains hundreds of them, drifting silently, almost never colliding with anything. Their masses are tiny, so tiny that for decades we assumed they might be zero, but their abundance is such that the combined weight of neutrinos across the cosmos is enormous. Like grains of sand on a beach, individually insignificant but together forming dunes and shores, neutrinos add up to a presence that matters. In the early universe, this presence acted as a kind of counterweight to matter's desire to clump together. When a region of space grew slightly denser, gravity tried to draw particles inward, gathering matter into knots that would later become galaxies and stars. But neutrinos, so light and so quick, resisted this gathering. They slipped away from overdense regions, spreading their energy outward, smoothing fluctuations like a hand brushing wrinkles from a sheet. The result was a universe where the largest structures were softened, stretched, and balanced by the ghostly influence of neutrinos. Without them, galaxies might have formed differently, clustered in other ways, perhaps producing a cosmos that looked utterly unfamiliar to us. To picture this, imagine trying to build a sandcastle on the beach while the tide comes in. The water does not destroy your efforts outright, but it smooths the sharp edges, blurs the walls, reshapes the contours. In the early universe, neutrinos played the role of that tide, flowing effortlessly through matter and ensuring that cosmic structures emerged not in jagged chaos, but in patterns shaped by their smoothing touch. As our understanding deepened, physicists realized that neutrinos might even be entangled with the greatest mysteries of all, dark matter and dark energy. Dark matter is the invisible glue that holds galaxies together, outweighing visible matter by a factor of 5, yet never glowing or scattering light. Dark energy is stranger still, an unknown force that seems to accelerate the expansion of the universe, pushing galaxies apart faster and faster. While neutrinos cannot explain all of dark matter or dark energy, their behaviour touches both mysteries. Their tiny masses contribute to the cosmic balance of matter, and their early influence on structure provides clues about how unseen components must behave. Some theories even suggest that neutrinos themselves could be part of the dark sector, a hint that the ghosts we already know may be relatives of even deeper shadows we have not yet glimpsed. This possibility is tantalizing but elusive. Neutrinos, by their very nature, resist being pinned down. They rarely interact, they oscillate between flavors, they evade capture. To link them firmly to dark matter or dark energy requires experiments of breathtaking subtlety, detectors of impossible patience. And yet, every time we measure neutrinos more carefully, every time we refine our models of how they shape the universe, we edge closer to answers about the unseen scaffolding of reality. Think of the cosmos as a cathedral under construction. The visible stones are the stars and galaxies stacked high into arches and spires. But beneath the scaffolding, the beams, the supports, the invisible framework, hold everything in place. Neutrinos, though ephemeral, were part of that scaffolding in the universe's youth. They helped guide the rise of structures that would one day become galaxies, clusters, and the great cosmic web. You do not see the scaffolding when you admire the cathedral, but without it the shape of the building would be entirely different. Even today, neutrinos continue to play their role. Their presence, faint though it seems, still contributes to the mass-energy budget of the universe. When cosmologists measure the rate of expansion, when they map the clustering of galaxies, they must account for the whispering influence of neutrinos. Their fingerprints are in the data, subtle but undeniable. And so, the ghosts that pass through you every second are not just passing strangers. They're also builders, architects whose work is hidden but essential. Perhaps there is a lesson here. The most powerful forces in shaping the universe are not always the loudest or most obvious. Photons dazzle us with brightness. Gravity asserts itself with unmistakable pull, but neutrinos shape silently, resisting notice even as they tilt the balance of everything. In life too, sometimes the unseen and the unheard leave the most lasting marks. A kind word remembered, a moment of silence shared, a presence that is felt without being proclaimed. These are the neutrinos of human experience, subtle influences that shape the structure of our days. So the next time you gaze at the night sky, imagine not only the stars but the invisible scaffolding that holds them in place. Imagine the neutrinos flowing like ghostly tides through the early cosmos, guiding matter into patterns, helping the universe take its familiar form. They are not gone. They are still here, woven into every cubic centimetre of space, part of the great balance sheet of existence. And though you cannot see them, though you will never feel their touch, they are among the oldest architects of the universe you call home. By now, you might feel a sense of awe at neutrinos, these elusive travellers that flow through you in endless streams, shaping the cosmos while leaving no trace of their passage. But for scientists, awe alone is not enough. If neutrinos are to tell us their secrets, about the sun, about supernovae, about the Big Bang itself, we must learn to listen to them. The problem is that listening to neutrinos is like trying to catch whispers in the middle of a storm, or like trying to count raindrops while standing in an ocean. They are everywhere, passing constantly, yet they almost never stop long enough to be noticed. To study them, we must build instruments, not of ordinary scale, but of extraordinary patience, detectors vast and silent, waiting deep underground or beneath the ice for the rare moment when a ghost particle reveals itself. One of the most famous of these instruments is Super Kamiokande in Japan. Hidden beneath a mountain, shielded from the distracting rain of cosmic rays that constantly bombard Earth's surface, lies a cavern larger than a cathedral. Inside is a tank filled with 50,000 tons of ultra-pure water. The walls of this tank are lined with thousands of sensitive detectors called photomultiplier tubes. They sit like watchful eyes gazing inward at the still water. Most of the time, nothing happens. Neutrinos pass by, billions upon billions every second, ignoring the water as if it were empty space. But every once in a while, a single neutrino collides with an atom in the water, producing a faint flash of light, a Cherenkov glow that ripples across the tank. In that instant, the detectors awaken, recording the signature of the ghost. From such rare flashes, scientists reconstruct the paths and energies of neutrinos, learning where they came from and what they have to say. It is a quiet kind of science. Unlike particle colliders that smash atoms together in violent bursts, neutrino observatories wait in stillness, patient as monks in meditation. The events they record are precious precisely because they are so rare. Each detection is a letter carried across impossible distances, a message from the sun, or from the atmosphere, or from a distant supernova. The observatory does not demand these messages, it simply listens. Further away, in the frozen wilderness of Antarctica, another kind of observatory listens in a different way. This is IceCube, a detector unlike any other on Earth. Instead of a water tank, IceCube uses the Antarctic ice itself as its medium. Scientists have lowered thousands of detectors deep into the ice, strings of photomultipliers stretching down more than 2 kilometers. The ice is so clear and so old that it makes a perfect lens. When a high-energy neutrino interacts with the ice, it creates a cascade of particles that emit Cherenkov light. Faint, but detectable. The detectors capture these flashes, and from the pattern, scientists can trace the path of the neutrino. What makes IceCube remarkable is its scale. It does not look like a traditional laboratory at all. From the surface, it seems like nothing more than a scattering of buildings and cables across the ice sheet, dwarfed by the endless white of Antarctica. But beneath that surface lies a volume of a cubic kilometre of instrumented ice, an observatory the size of a city. It listens not just for neutrinos from the sun or the atmosphere, but for the most energetic neutrinos the universe can produce. Neutrinos born in distant galaxies, in the tumult of black holes feeding, or in jets of matter blasted from cosmic accelerators we do not yet fully understand. To imagine how these observatories work, think of vast dark lakes, their waters undisturbed, their surfaces smooth and silent. Around them stand watchers, waiting for ripples that may or may not come. Hours pass, days pass, sometimes weeks pass without a single event. And then, at last, the faintest ripple appears, a flash of light, a whisper of energy, and in that moment the watchers lean forward, listening, recording, interpreting. It is a science of patience, of trust that the universe will eventually speak. The images that come from these observatories are not photographs in the ordinary sense. They are reconstructions, maps of flashes, abstract but beautiful. A streak of light across the detector might mean a neutrino has passed straight through, leaving its trace like a shooting star in a frozen sky. A sphere of expanding light might mark a collision at rest, like a ghost suddenly deciding to tap on the glass before disappearing again. These pictures are both scientific and poetic, glimpses into a world usually hidden, shapes drawn by particles that almost never consent to be seen. And why do we go to such trouble? Because the rewards are profound. By detecting solar neutrinos, we confirm our understanding of how stars shine. By catching neutrinos from supernovae, we witness the very mechanics of stellar death. By recording high-energy neutrinos from beyond the galaxy, we open windows into extreme physics that no experiment on Earth could replicate. Each detection is a message from places we cannot reach, a story told by particles that do not scatter, do not delay, but travel in straight, unbroken lines from their origin to us. The act of building these observatories also speaks to something deeply human. We are creatures who long to know, who are willing to dig into mountains and bore into ice, who are patient enough to wait years for the faintest signal. It is as though we've created ears for the Earth, listening for whispers carried by neutrinos, whispers that tell us of fires burning at the hearts of stars and of cataclysms unfolding at the edge of the universe. And so, the hunt for neutrinos is not really a chase at all. It is more like meditation, a stillness in which we allow the universe to come to us. The ghosts will not be caught in nets or traps. They cannot be herded or forced. They will pass through us regardless, unbothered and untouchable. All we can do is create the conditions to notice them, to mark the rare moments when they choose, by chance, to leave a trace. Perhaps there is something comforting in this. The universe is vast and mysterious, filled with energies and forces we cannot control, yet even in its silence it gives us clues. By building great quiet instruments, underground lakes of water, frozen cubes of Antarctic ice, we show our willingness to listen. And in that listening the cosmos answers, not loudly, not often, but in flashes of light so faint that only the most patient of watchers can see. If special relativity taught us that time is linked to speed, then general relativity extends the lesson further. Time is also shaped by gravity. This idea can be difficult to wrap your mind around because gravity, in everyday life, feels so ordinary. You drop a cup and it falls. You step on the ground and it holds you. The pull of the earth is constant, steady, something you rarely notice except when you stumble or when your muscles ache after climbing a hill. But beneath that familiar tug lies a profound secret. Gravity is not just a force, it is the bending of space and time itself, and when space bends, time bends with it. To begin imagining this, think of a stretched sheet of fabric. Place a heavy ball in the middle, and the fabric dips, curving downward. Now roll a smaller ball nearby, and it circles the dip, pulled not by an invisible string but by the curvature of the fabric itself. This is the picture Einstein offered. Matter tells space-time how to curve, and curved space-time tells matter how to move. But hidden within the picture is another truth. If space is curved by gravity, then time, which is woven into the same fabric, is curved as well. Clocks do not tick at the same rate everywhere. A clock near a heavy mass ticks more slowly than a clock far from it. You can actually experience this difference, not in dramatic ways, but in tiny, measurable ones. Imagine two identical clocks, one at sea level and one on top of a mountain. The clock closer to Earth's centre, deeper in its gravitational well, will run a little slower than the one higher up. The difference is minuscule, measured in nanoseconds, but it is real. Scientists have tested it again and again with atomic clocks, the most precise instruments we possess. The results always confirm Einstein's insight. Gravity bends time. Think of a line at a busy market. Perhaps you're waiting for bread, and there are several queues. One line moves quickly, the other slowly, though both are made of people waiting for the same thing. Gravity does something similar to time. Where the gravitational field is strong, time's line moves slowly. Where gravity is weak, time's line moves faster. Everyone is still waiting for bread. Everyone's moments are still passing, but the pace is different depending on where you stand. The effect grows stronger near massive objects. Around the Earth, the slowing of time is slight but measurable. Around a neutron star it becomes extreme, and near a black hole it becomes almost absolute. If you could hover safely near the event horizon of a black hole, while your friend remained far away, you would find that your seconds stretched into their hours. For you, the clock ticks steadily, heartbeat after heartbeat, moment after moment. For your friend, however, you appear to move in slow motion. your signals delayed, your time stretched almost to a standstill. The closer you approach the horizon, the more dramatic the effect becomes, until at the edge, time as we know it effectively stops. Black holes, then, are not just exotic objects, they are laboratories for time itself. They show us what happens when gravity bends the fabric of space-time to its limit. To imagine standing at the threshold of such a place is to imagine watching the universe race ahead while your own time crawls. A second for you could be centuries outside. You could, in theory, witness the far future unfold in the blink of an eye, though of course you would never return to tell the tale. Even without black holes, the bending of time is part of our everyday technology. The satellites that orbit Earth, providing the signals for GPS, experience weaker gravity than we do on the surface. Their clocks tick slightly faster. Engineers must correct for this difference. Otherwise, your navigation app would drift, placing you kilometers away from your true location. Every time you check your phone for directions, the software is quietly accounting for the warping of time in Earth's gravitational field. Relativity is not a distant abstraction, but an invisible thread woven into your daily life. The philosophical weight of this truth is enormous. Time, which we once imagined as absolute, identical for all, is revealed as local and relative. Your now is not my now. Your second is not quite my second, depending on where we stand and how we move. We are bound by the same universe, but the tempo of our lives can be subtly different. It is a humbling thought, to know that the universe is not ticking with a single universal clock, but with countless local rhythms, each tied to its own circumstances of motion and gravity. And yet, there is a strange comfort in it as well. Just as no two people experience a day in exactly the same way, one finds it long, another finds it short, no two places in the cosmos experience time in exactly the same tempo. The diversity of time's flow is part of the fabric of reality. Perhaps that is why we treasure moments so deeply. They are not repeatable, not universal, but unique to us, to where we are, to how we move and feel. So the next time you wait in line, or sit on a train that seems to crawl while another flashes past, imagine the universe as a series of cues, each moving at its own pace depending on the gravity around it. You're standing in one line, I in another, and our clocks, though similar, are not quite in sync. Yet together all these different tempos form the music of the cosmos, a harmony created not by uniformity, but by variation. Gravity slows time, but in doing so, it enriches the universe with diversity. And with this, we see that time is not only stretched by speed, as Einstein's special relativity taught us, but also by the weight of matter itself. Space and time are partners, curved together. The earth beneath your feet, the star above your head, the black holes hidden in distant galaxies, all of them shape the flow of time. It is not absolute. It is not fixed. It bends with the gravity of the cosmos, making each second a little different depending on where you stand. When you wake in the morning and glance at the clock, it feels natural to assume that the present moment is something absolute, a shared reality that everyone on Earth experiences together. You imagine that while you sip your tea, another person thousands of miles away is stirring their own cup, and though their morning may be your evening, you both inhabit the same now. The idea is so intuitive that we rarely question it. Surely the present is universal. Surely there is one great cosmic clock that defines what exists at this very instant. But relativity quietly tells us that this intuition is an illusion. There is no single, universal now. What is present for you may not be present for someone else, depending on where you stand and how you move. To appreciate this, imagine two people standing far apart, watching a flash of lightning strike at a distance. If they are standing still relative to one another, they might agree on when the flash occurred. But if one of them is moving, say on a speeding train while the other remains on the ground, Their judgments of simultaneity can differ. The passenger may insist the flash happened a little earlier, while the observer on the ground claims it was a little later. Both are correct, from their own perspectives. Relativity allows no single master verdict on which moment is truly now. This idea is subtle, but it reshapes our picture of reality. It means the universe is not like a single film reel, spooling through frames one by one, with everyone watching the same scene at the same time. Instead, it is more like a vast patchwork quilt, each patch representing a slice of space-time stitched from a particular perspective. Your now is one patch, my now is another, and they do not always line up neatly. The quilt is whole, but it does not present a single shared present moment. At first glance, this can feel disorienting. You may wonder, does this mean the present does not exist? Does it mean that time itself is an illusion? Not quite. What it means is that the present is local, not universal. You experience your now within your own frame of reference, and I experience mine in mine. They overlap when we are close and still relative to each other, but diverge when distance or motion become significant. The farther apart two observers are and the faster they move relative to each other, the less agreement there is about what counts as now. You may find this easier to visualize if you think about long-distance communication. Imagine a message sent between Earth and Mars. Even travelling at light speed, the message takes minutes to cross the gulf. The Martian receiving the message does not share your exact present. They inhabit a moment slightly behind, waiting for your words to arrive. Add motion into the equation, and the concept of simultaneity frays even further. Einstein's insight into this relativity of the present was one of the most radical shifts in human thought. Before him, philosophers and scientists alike tended to believe in absolute simultaneity, a universal present that stretched across the cosmos. With relativity, that comforting certainty dissolved. There is no single cosmic moment, only countless local perspectives, each with its own version of what is happening now. Yet, rather than being unsettling, there is a quiet beauty in this view. It tells us that reality is richer than our everyday intuitions suggest. Just as different cultures imagine time as cyclical or linear, different observers carry their own patches of present. Together, they weave a fabric that is not rigid but supple, able to accommodate many viewpoints without contradiction. Think of it like a symphony performed in a vast concert hall. From where you sit, the violins reach your ears just a fraction earlier than the cellos, depending on where you are positioned. Someone on the other side of the hall hears the arrangement differently. No listener experiences the same music in precisely the same way. Yet all are hearing the same symphony, woven from the same notes. The relativity of now is like that. Each observer experiences their own timing of events, and together these experiences form the full harmony of space-time. There is also something deeply human about this realization. We often speak as though we share the present with others, but in truth, even in daily life, each person's now is unique. Your memories, your awareness, your emotional state, all of these shape how you perceive the moment. For one person, a day may drag endlessly. For another, the same day may vanish in a blur. Relativity extends this subjectivity from psychology into physics itself, telling us that the difference in nows is not just a matter of feeling, but a fundamental property of reality. This perspective can soften the urgency of time. If there is no single universal present, then perhaps the anxiety of trying to hold on to now can ease. Your now is yours to live, fully and quietly, without needing it to align perfectly with anyone else's. The universe is not a strict clock demanding coordination. It is a vast quilt, allowing many rhythms, many perspectives, all stitched into a coherent whole. So the next time you look at a clock and feel the pressure of its ticking hands, remember that even those hands are part of a local rhythm, one among countless others in the cosmos. Your now is precious not because it is the same as everyone else's, but because it is uniquely yours, stitched from your motion, your position, your perception. In the grand quilt of space-time, it is one patch among many, different but essential, contributing to the beauty of the whole. If the cosmos bends and reshapes time according to speed and gravity, then within you there is another kind of timekeeper, quieter, but no less profound. You carry a clock inside your chest, one that ticks not with gears or with equations, but with pulses of life. Your heartbeat, steady and unbidden, marks the passage of your days in a rhythm so familiar you rarely notice it. Every second or so it sounds its quiet note, circulating blood, sustaining, organs, keeping you alive. It has been with you from the moment before your first breath, and it will continue until your very last. In its constancy, your heart is the simplest and most faithful clock you own. But the body does not rely only on this drumbeat. There is a deeper rhythm woven into your cells known as the circadian cycle. Every living thing on Earth, from the smallest algae to the tallest trees to human beings, has evolved with this cycle, tied to the turning of the planet and the rising and setting of the sun. Hormones surge and fall, body temperature shifts, alertness waxes and wanes, all in a rhythm that repeats roughly every 24 hours. It is why you feel sleepier at night, why your mind sharpens in the morning, why jet lag unsettles you when you travel across time zones. The circadian rhythm is a whisper from Earth itself, telling you when to wake, when to rest, when to dream. And yet, even these biological clocks are not absolute. They are as pliable as the physics of time dilation, though in a gentler way. If you stay up late staring at glowing screens, your rhythm shifts. If you travel to a faraway country, your internal clock lags behind, stumbling for days until it adjusts. The cycle is resilient but not unchangeable. It is like a river that knows its course, but allows for meanders and eddies. Beyond the circadian, there are countless other rhythms within you. Cells divide in cycles, neurons fire in bursts, breaths rise and fall, each system keeping its own time. Some rhythms are quick, like the flutter of electrical impulses in your brain. Others are slow, like the monthly tides of hormones or the gradual renewal of bones and tissues. Together they weave a symphony of biological time. You're not governed by a single clock, but by an orchestra of them, some loud, some quiet, all playing together to create the music of your life. Memory, too, acts as a kind of clock, not in the way of ticking seconds, but in how it stretches or compresses the fabric of your experience. A joyful day passes quickly while it unfolds, but looking back it often feels full, as though time was abundant. A boring day, by contrast, drags while it happens, yet shrinks to a blur in memory. Your mind, in this way, is not a neutral observer of time, but a sculptor of it, reshaping your sense of duration according to attention and emotion. The physics of relativity tells us that motion and gravity alter time. The psychology of living tells us that happiness, sorrow, novelty and routine do the same. Think of childhood summers. Each day felt endless, wide and overflowing with possibility. The weeks stretched on, filled with new experiences that imprinted themselves deeply. In memory, those summers are vast landscapes. Now think of a recent month of adulthood, a month filled with commutes, repeated tasks, familiar chores. It may feel as though it disappeared quickly, slipping past before you noticed. The difference is not in the clock on the wall, but in the way your brain recorded the moments. More novelty means more memory, and more memory makes time feel fuller. Less novelty, fewer markers, and time collapses, vanishing behind you. This is why your body and mind are not just passengers of time, but creators of it. You carry within you not just the physics of heartbeat and circadian rhythm, but the personal, subjective shaping of memory and emotion. You are, in a sense, a time machine, but not one that leaps across centuries or races at the speed of light. Rather, you bend and stretch your own experience of time every day, sometimes without realizing it. There is a quiet poetry in this, The clocks of physics tell us about the universe as a whole, how black holes slow time, how photons escape time altogether. The clocks of the body tell us about the intimacy of living, how breaths, beats, cycles and memories define our existence. Together, they form two layers of truth. One is cosmic, written in equations and galaxies. The other is personal, written in heartbeats and stories. Both are real, both are essential, and both remind us that time is never as simple as the ticking of a second hand. So the next time you feel your pulse on your wrist or listen to your breath slowing as you drift towards sleep, think of them as clocks. Clocks not on a wall but within you. They are the measure of your own local universe, marking the passage of moments in ways that belong only to you. The stars above bend time with gravity. The neutrinos around you stretch time with their near-light journeys, but your own body carries its rhythms too. They are smaller, gentler, but no less profound. And perhaps this is why moments matter so deeply, because time is not only measured in seconds and minutes, but in heartbeats, in breaths, in memories made and remembered. You're not just moving through time, you're writing it inside yourself, carrying it in your cells, your mind, your heart. In this sense, you're a library of moments, a chronicle written not on paper, but in the quiet rhythms of life. Each heartbeat is a page, each breath a line, each memory a chapter. Together they form the story of who you are, lived 1 second, one rhythm, one beat at a time. So far we have followed time through the laws of physics, seen it bend under the weight of gravity and nearly vanish at the speed of light. We have watched neutrinos skim the edge of timelessness, and we have listened to the heart as it beats its quiet rhythm inside your chest. But there is another dimension of time that is as powerful and as mysterious as any cosmic law, and it lives not in the stars or the equations, but in your own mind. This is the time of perception, the elastic and often unpredictable flow that stretches and contracts depending on what you feel, what you remember, and what captures your attention. You know this truth already in the most ordinary moments. Think of waiting in a doctor's office with nothing to do but stare at the wall. Minutes crawl by, each second lengthened until it feels heavy and endless. Now compare that to an evening spent laughing with friends or wandering in a city you've never visited before. Hours dissolve like mist, and when you glance at the clock you're startled at how quickly time has gone. In one case, time was sluggish, reluctant to move. In the other, it was swift and elusive. Yet the same number of minutes passed in both. The clock did not change, but your experience of it did. Psychologists have studied this phenomenon and found that attention is key. When your mind is focused outward, immersed in novelty or pleasure, you record fewer individual moments, and so the interval feels shorter in retrospect. But when you are bored or anxious, your attention narrows, watching each second as it drips by, and the interval feels longer. The result is that time in the mind is not smooth but elastic, stretching and shrinking according to how you inhabit it. Memory adds another twist. As children, summer seemed endless. Each day was filled with discovery. New games, new sights, new lessons, new friends. Because everything was new, your brain stored countless details, and when you look back, those summers feel vast and sprawling. As an adult, routine compresses experience. Days filled with repetition are not stored as richly, so when you look back, the weeks blur into one another, making months or even years feel as though they passed quickly. To the brain, novelty expands time in memory, while routine compresses it. Emotions also tint your perception of duration. Fear stretches time. In a sudden accident, a fall, or a moment of danger, you may feel that time slowed down, each detail captured with unusual clarity. Joy, by contrast, often accelerates it. A wedding, a holiday, a long-anticipated reunion can pass in a blink, leaving you almost bewildered that it is already gone. Sadness has its own texture, sometimes stretching days into long grey corridors, sometimes collapsing them into indistinct haze. Your mind does not measure time with atomic precision, it measures it with the colour and weight of experience. This is not to say that the clock on the wall is wrong. Physics continues its steady march, seconds piling on seconds in unchanging rhythm. But inside your head, time becomes subjective, deeply personal. The physics of time may be universal, but the psychology of time is individual. Two people in the same room, listening to the same story, may walk away with entirely different impressions of how long it lasted. For one, it may have flown. For the other, it may have dragged. Both are correct, because both are speaking of the time they lived in the mind. Consider the state sometimes called flow. It happens when you're completely absorbed in a task. Painting, writing, gardening, even solving a problem at work. In flow, hours pass unnoticed. You look up and realise that an afternoon is gone, though it felt like only minutes. Your attention was so immersed that the ordinary markers of time vanished. In a sense, you stepped outside of your own awareness of duration, living not in seconds, but in pure activity. Compare that with insomnia, lying awake at night, watching the ceiling, every minute dragging into the next. The contrast could not be sharper. In one, time vanishes. In the other, time refuses to move. The mind, then, is not only a passenger of time but also its sculptor. It bends the flow according to attention, memory and emotion. This elasticity makes life richer, though it also makes it more complex. It explains why a year of childhood feels longer than a year of adulthood, why vacations seem short while they are happening but long when remembered later, why trauma leaves scars not just on the body but on the perception of time itself. And perhaps there is a gentle lesson here. If novelty expands time in memory, then perhaps seeking new experiences can make life feel fuller. If routine compresses time, then perhaps breaking routine, walking a new path, tasting a new food, learning a new skill, can stretch your perception of life's fabric. You cannot change the physics of seconds and hours, but you can shape the way they are lived. Think of your life as a book. The clock is the binding, setting the number of pages, but you are the author of how much is written on each one. In some chapters, the pages are sparse, with little to distinguish them, and when you flip back, they seem to vanish. In others, the pages overflow with detail, with vivid colour, with novelty, and when you flip back, they stretch across the memory like epic chapters. Time in the mind is like that, an art of storytelling, written moment by how you live. So as you listen to this, allow yourself to soften into your own perception of time. Notice how the minutes may already feel different from the clock's tally. The science of neutrinos and the physics of relativity may tell us how the universe measures time, but your own mind tells you how you live it. Both are true. Both matter. And in the quiet of night, as you drift towards sleep, perhaps the most important time is not the cosmic kind, but the personal kind. The rhythm of breath, the elasticity of memory, the soft subjective river that carries you into dreams. If physics teaches us that time is flexible, and psychology shows us that it is elastic in the mind, then human culture reveals yet another layer of complexity. We do not all imagine time in the same way. Across history and across civilizations, people have painted very different pictures of what it means to live in time. Some have seen it as a circle, endlessly returning, while others have drawn it as a line, marching forward. Some have treated it as a precious commodity to be counted and saved, while others have treated it as a landscape to wander freely. These cultural metaphors may not change the ticking of a clock, but they profoundly shape how time feels in daily life, how societies are organised, and how individuals experience their days. Let us begin with the cyclical view. In many ancient cultures, time was not an arrow, but a wheel. The sun rose and set in a loop. The seasons followed one another in unending rotation. Planting led to harvest and back again. and human life was seen as part of this eternal cycle. Birth was followed by death, which was often understood not as an end but as a return. In Hindu thought, the great cycles of time are vast beyond comprehension, with universes themselves being created, destroyed, and created again, endlessly. The Maya of Central America built calendars that emphasized cycles, great wheels within wheels, where human history itself was folded into repeating patterns. For peoples tied closely to the land and the sky, cycles were the most natural metaphor. Life returned like the moon, waxed and waned like the seasons, flowed endlessly like rivers that circle back as rain. Contrast this with the modern Western view, which tends to see time as linear, influenced by traditions in Judaism, Christianity, and Islam. History came to be understood as a story with a beginning, a middle, and an end. Creation, life, judgment, destiny. These ideas gave rise to a narrative of time that moved in one direction only. The Enlightenment and the Industrial Revolution deepened this sense, turning time into a measure of progress. The future was not a return to the past, but a place to be reached, a goal to be achieved. This linear view now dominates much of the globalized world, where calendars and schedules carve time into straight lines, into deadlines and plans, into histories that march forward without circling back. Neither view is entirely right or wrong. Both are lenses, and each brings a certain truth. The cyclical view captures the repeating patterns of nature, the turning of the earth, the beating of seasons, the rhythms of birth and death. The linear view captures the sense of uniqueness, the fact that moments do not return, that your life is a one-way journey from birth to death. Together, they remind us that time can be understood as both circle and arrow, both repetition and progression. Language itself reinforces these differences. In English, we often speak of time as money. We spend it, save it, waste it, invest it. This metaphor encourages efficiency, a sense that time is scarce and must be managed carefully. In other languages, time is spoken of as a resource flowing toward us, or as a space we inhabit. In the Aymara language, spoken in the Andes, the past is described as being in front of us, because it is visible and known, while the future is behind us, unseen and mysterious. When speakers gesture about the future, they wave behind their backs. To English speakers, this feels reversed, but to the Aymara, it is perfectly logical. You face the past because you can see it. The future comes from behind because you cannot. Consider also the difference between cultures that prioritize punctuality and those that prioritize presence. In some societies, being on time means arriving at the precise minute scheduled. To be late is to disrespect the clock, and by extension, to disrespect the people waiting. In others, time is treated more fluidly. A meeting begins when everyone arrives. A conversation continues as long as it needs to, regardless of the hour. Neither approach is inherently better. They reflect different cultural relationships with time. In one, the clock is the master. In the other, human connection is the master, and the clock is a suggestion. The Industrial Revolution amplified the dominance of clock time. Factories required shifts, trains required timetables, businesses required precision. Time was chopped into uniform hours and minutes, measured and enforced by bells and whistles. The world became synchronized in ways it had never been before. Before this era, most people lived by natural rhythms: dawn and dusk, planting and harvest, fasting and feasting. With industrialization came the global clock, the rise of time zones, the insistence on uniform schedules. Humanity, for the first time, began to live by the same hours, coordinated across nations. Time became mechanical, regimented, efficient. And yet, beneath this mechanical layer, cultural differences still thrive. Mediterranean societies, for instance, often value the long lunch, the siesta, the slower unfolding of the afternoon. Northern societies may prize punctuality and efficiency, filling every hour with tasks. In Japan, there is the concept of ma, the space between, the pause that gives shape to action. In Africa, some traditions emphasize event time, where gatherings begin when everyone is ready, not when the clock demands. Each of these approaches reflects a truth. Time is not only measured but lived, and how we live it is shaped by the metaphors and traditions we inherit. You too carry a culture of time within you. It informs whether you feel anxious when someone is late, or whether you feel relaxed seeing no need to rush. It shapes whether you treat a day off as wasted if nothing was achieved, or as cherished if it was filled with rest and presence. It influences whether you think of life as a straight line marching to a destination, or as a series of circles that echo and return. So the next time you feel frustrated by a delay, or hurried by a schedule, pause and remember. The very idea of what it means to be on time is not universal. It is a cultural construct, one of many possible ways to live within the flow of seconds. The universe itself has no preference. The stars turn, the earth spins, the neutrinos pass through us unbothered by clocks or calendars. We are the ones who drape time with meaning, who stitch it into stories of progress, cycles or presence. Perhaps that is the quiet gift of recognizing cultural time. It reminds us that there is not one way to live within the river of moments. There are many, and each has its own wisdom. The circle teaches patience, the line teaches urgency, the metaphors of money teach efficiency, the metaphors of space teach presence. Together they form a mosaic of human imagination, a testament to our need not only to measure time but to understand it, to shape it into stories that guide how we live. When you think about light and neutrinos and the strange laws of relativity, it is easy to feel small. Time at those scales bends and twists in ways so unlike your everyday life that you might wonder whether the seconds you count on your watch mean anything at all. Photons slip outside of time entirely. Neutrinos drift so close to timelessness that their clocks hardly move, and black holes bend time until it nearly freezes. Compared to those extremes, human time can seem fragile, temporary, almost trivial. And yet, perhaps it is exactly this fragility that makes it beautiful. Perhaps time for us is not a limitation but a gift, one that gives shape and meaning to moments that would otherwise collapse into nothing. Consider music. A song is not made of sound alone but of pauses between sounds. Without silence, without duration, there is no rhythm, no melody. Notes require time to unfold. A symphony compressed into a single instant would be nothing but noise, indistinguishable and overwhelming. In the same way, life requires the pacing of time. Without minutes and hours, without the slow unfolding of days, there would be no stories, no growth, no memory. The very fact that you cannot live outside of time, that you must move through it moment by moment, is what allows you to savour a conversation, to remember a sunset, to look forward to tomorrow. Slowness, then, is not a flaw of human life, but its essence. Imagine if you lived like a photon, collapsing billions of years into an eternal now. There would be no waiting, but also no anticipation, no savouring, no unfolding of joy. Imagine if you lived like a neutrino, with time stretched so far that the difference between moments was almost erased. There would be no hurry, but also no rhythm, no sense of change. It is only at human speed, with seconds and minutes measured by heartbeats and breaths, that the world becomes a place of experience. This is why some of the most precious moments in life are those when time seems to slow. Sitting at a table with someone you love, sharing a meal without rush, walking beneath trees, noticing how the leaves stir in the breeze, listening to rain fall against a window. In these moments, the clock on the wall may tick the same, but your mind softens. stretching the instant into something larger than itself. Slowness makes room for presence, and presence makes room for meaning. Our modern world, with its screens and schedules and ceaseless demands, often pushes against this gift. We are told to hurry, to optimize, to fill every hour with tasks and goals. Time is measured in productivity, in deadlines met, in emails sent. But beneath this rush, there remains the quiet truth. The richest moments are rarely the fastest. They are the ones in which time is allowed to linger, to flow gently instead of rushing forward. Childhood summers felt long, not because the clocks were different, but because you allowed them to stretch, because novelty and attention filled them with detail. The art of reclaiming slowness is, in some ways, the art of returning to that childlike openness. Even nature reminds us of this lesson. Trees grow slowly, rings expanding year by year, marking decades with patience. Rivers carve valleys over millennia, drop by drop, flow by flow. Mountains rise and wear down, not in days but in spans longer than civilizations. The cosmos itself is patient, stars burning for billions of years, galaxies colliding on scales beyond human imagination. Against this backdrop, your life is brief, but its brevity is not a curse. It is the very reason moments shine so brightly. A firefly glows for only a night, but its light is no less beautiful for its shortness. And so, to live within time is to accept slowness as a companion. You cannot race through every moment, nor can you escape into timelessness like a photon. What you can do is embrace the pace you are given. You can pause for breath, for wonder, for the simple act of noticing. You can let a conversation run long, let sunset linger, let yourself drift without checking the clock. These are not wastes of time. They are the very substance of life. Philosophers have often noted that to live well is to live attentively, and attention requires slowness. You cannot notice a flower if you rush past it. You cannot savour music if you only skip from note to note. To attend is to slow, and to slow is to receive the gift of time in its fullest. Perhaps this is why sleep itself, the quiet slipping away of hours in which you are unaware, is so necessary. It feels unproductive, a blank stretch in which nothing gets done. But it is in those slow hours that memory consolidates, that the body repairs itself, that the mind dreams. Even unconscious slowness has purpose. Time's gift is not always in the doing, but often in the waiting, the resting, the drifting. So the next time you find yourself wishing time would move faster, pause and consider. It is the very slowness of time that allows you to experience anything at all. The rush of light is eternal. The near timelessness of neutrinos is cosmic, but the pace of your life, measured in heartbeats, in footsteps, in breaths, is human, and it is enough. Let time be slow tonight. Let each word arrive gently, each thought linger, each breath remind you that you're living within the gift of duration. The universe may be timeless at its edges, but here, in this quiet moment, the seconds are yours, unfolding softly, one after another, shaping the story of your life. All throughout this journey, we have wandered through the mysteries of time, how it bends under gravity, how it slows near the speed of light, how it disappears entirely for photons, and how it stretches almost beyond recognition for neutrinos. We have touched on the clocks inside your body, on the ways cultures imagine time, on the elasticity of memory and perception. Each piece has been like a thread woven into a tapestry, and now we begin to see the whole picture. At the centre of this picture are two messengers, two travellers that speak to us in silence. Photons, the eternal couriers of light, and neutrinos, the ghostly witnesses of creation and catastrophe. They move through the universe in ways we cannot, and in their movement they whisper something profound about the nature of time itself. Consider photons first. They are the bright carriers of every image you have ever seen, from the sunlight streaming through your window to the distant shimmer of galaxies billions of light years away. Each photon has no rest mass. It cannot stop, it cannot slow, it cannot exist at any speed other than the speed of light. For them, time is not a river. It is not even a ripple. From the moment they are emitted to the moment they are absorbed, no duration passes. The star that shone its light in the early days of the universe and the photon that reaches your eye tonight are bound by the same instant. Billions of years may have rolled by for galaxies and planets, but for the photon, it has only ever been now. This makes every act of seeing extraordinary. When you gaze at the sky, you are not just witnessing distant history. You are receiving messages from photons that have travelled without delay from their perspective. The light of a galaxy that left when the Earth was young arrives as if it never left at all. The glow of your bedside lamp, generated just moments ago, reaches you instantly in its own frame. For photons, the entire universe is a single painting, all its distances and durations collapsed into one eternal canvas. To see then is to touch timelessness. Every glimmer of light is a messenger that has crossed the cosmos outside of time. Now think of neutrinos. They are less familiar, less visible, but no less remarkable. They're born in the nuclear furnace of the sun, in the violent collapse of supernovae, in the earliest moments after the Big Bang. They are not massless, but their masses are so faint, so ghostly, that they come within a breath of light speed. Because of this, time for them is stretched almost flat. From their perspective, moments blur and distances contract. A neutrino travelling from a distant star may experience only a faint heartbeat of duration, even though millions of years have passed for us. They are not entirely timeless like photons, but they live on the very edge, skimming along the border between the time-bound and the time-free. Unlike photons, neutrinos can slip through places light cannot. Light is scattered, absorbed, delayed. Neutrinos glide through stars, through planets, through you, without pause. Trillions pass through your body every second, witnesses to cosmic events you will never see, carrying postcards from the heart of the sun, from the collapse of ancient stars, from the fiery dawn of the cosmos. Most will never interact, never leave a trace, yet they are here, sharing your present, brushing past you silently. Together, photons and neutrinos form a pair of messengers, one bright and visible, the other invisible and ghostly, both reminding us that time is not as rigid as we think. For photons, it vanishes. For neutrinos, it nearly dissolves. For us, it remains steady, measured in heartbeats and clocks, yet even then, it bends and flexes under speed, gravity and perception. Time, it seems, is not a universal stage but a shifting fabric, stitched differently for each traveller. To hold this thought is to feel a deep kind of wonder. Right now, in this quiet moment, photons are bouncing off the walls of your room, carrying images to your eyes. At the same time, neutrinos are flowing through you by the trillions, messengers from the sun and from ancient explosions. You're surrounded by timeless travellers, immersed in a sea of particles that care little for the seconds and minutes that govern your life. They remind you that while you live in time, you're also connected to things that move beyond it. Imagine them as rivers flowing through you. Photons are bright streams, sparkling with colour and warmth, painting the world so you can see. Neutrinos are shadow rivers, invisible currents that slip through mountains and oceans as if they were air. Both flow continuously, day and night, across every corner of the universe, and you, without effort, are part of their journey. The message they carry is simple yet profound. Time is not absolute. It is flexible, relative, perhaps not fundamental at all. The universe does not tick with a single clock. Instead, it allows each traveller its own rhythm. Frozen timelessness for photons, stretched instants for neutrinos, flowing mints for human beings. None is wrong. All are true. The universe is a harmony of tempos, a symphony where each instrument plays at its own pace. So as you listen tonight, let yourself soften into this thought. You are part of a cosmos where timeless messengers move through you constantly. The light you see and the ghosts you cannot feel are reminders that reality is larger, stranger, and more beautiful than any one perspective can capture. You do not need to solve the puzzle or hold all the equations. It is enough to know that while you count seconds, while you remember days, while you look forward to tomorrows, there are companions that slip through time differently, carrying with them the stories of the stars. And in that knowledge, perhaps there is comfort. For though your own time is finite, though your days pass quickly, you're always surrounded by eternity. Photons and neutrinos flow through you now, eternal travellers and ghostly witnesses, and in their passage they remind you that you are not separate from the vast universe, but threaded into its fabric, woven into its timeless song. As this long wandering draws to its close, let us gather all the threads we have traced and lay them gently at your side like blankets pulled over a resting traveller. We have journeyed with photons who know no waiting, slipping from the hearts of stars to the backs of your eyes without ever pausing in their own frame of existence. We have followed neutrinos, ghost-like companions that skim the boundary of timelessness, brushing through you in numbers too vast to imagine, carrying memories of both cataclysm and creation. We have bent time with gravity, slowed it with speed, stretched it with memory, and reshaped it with culture. And through it all, one truth has emerged, both simple and profound. Time is not fixed. It is flexible, relative, woven differently for each traveller, whether particle or person. And yet, despite these mysteries, your own time remains precious because it is your own. You do not move outside of time as photons do, nor do you skim its edge as neutrinos do. You live within it, heartbeat by heartbeat, breath by breath. You measure it not in infinities, but in mornings and evenings, in seasons that pass, in stories remembered. The brevity and slowness of human time, which may seem so small against the backdrop of the cosmos, are exactly what make it meaningful. It is only because you move step by step, second by second, that you can savour, anticipate, and remember. Time gives you music instead of noise, stories instead of static, lives instead of an eternal, formless now. There is something humbling and beautiful in knowing that even as you live inside time, you carry pieces of timelessness within you. The atoms in your body were forged in ancient stars, some in explosions that predate the sun itself. Neutrinos from the very birth of the universe still pass through you, reminders that you are linked to moments far older than Earth. Every breath you take carries oxygen molecules shaped by plants and oceans. Every cell in your body whispers rhythms that tie you to the turning of the planet. You are both a creature of time and a vessel of eternity, walking a path that stretches from the first second of the cosmos into a future yet unwritten. Perhaps that is the quiet secret of time. It is not just a constraint, but a gift. Without it, there would be no rest, no wonder, no dreaming. If you lived like light, collapsing billions of years into an instant, you would never wait, but you would also never savour. If you live like a neutrino, stretched so thin that instants blur together, you would never hurry, but you would never feel change. It is only at the human pace, slow enough to notice, long enough to remember, that life becomes rich with meaning. Time allows you to linger over a conversation, to marvel at a sunset, to hope for tomorrow. It allows you to rest, to dream, to wonder, and tonight it allows you to drift into sleep. The photons will continue their journeys without pause. The neutrinos will continue to flow through you, silent and unbothered. The galaxies will keep spinning. The stars will keep burning. The cosmos will keep expanding. Time on those scales will stretch and bend as it always has. But here, in this quiet moment, your only task is to let go, to trust the gift of slowness, to allow the minutes to soften into dreams. You are, in a way, a little traveller through time yourself. You walk forward without stopping, never able to turn back, always carried onward by the current. You do not need to race. You do not need to grasp. It is enough to float, to rest in the flow, to know that each moment is unique and unrepeatable. The photons remind you that some things escape time. The neutrinos remind you that some things almost do, but your own path is different. Yours is measured and gentle, long enough to hold love and memory, short enough to be precious. So as you close your eyes and let your thoughts fade, imagine yourself surrounded by these timeless messengers. Imagine photons falling like gentle rain across your pillow, neutrinos flowing like invisible streams through the room. They pass through you constantly, carrying stories from stars and from the very beginning of time. You're wrapped not only in blankets, but in the fabric of the cosmos, threaded with particles that know no waiting, no delay. You're never separate from the universe. You're always part of its vast, ongoing story. And perhaps in that thought, there is comfort. You move through time, but you also carry eternity within you. The cosmos is not distant. It is here, in your body, in your breath, in the quiet hum of neutrinos, in the gentle glow of light. Sleep now, little traveller through time. Rest in the river that carries you, knowing that you are surrounded by messengers who remind you of both your smallness and your grandeur. And with that, we've finished tonight's journey. If you're awake, I'm glad you stayed. If you've drifted off, that was the point all along.